It's a pleasure to be here. When I was a student, it would be very interesting to see all these people come through, give talks, and never contemplated I would be doing the same someday. But it's a pleasure to be here, and a great honor to be here. What I'm going to talk about is, some work that we are doing, but really sort of much more sort of a, vision of how I think we're going to be computing running programs in the future. And what I'd like for you to do is ask me questions at any time. Please stop and ask me questions. If I don't get questions, then I will have to have a chat with the faculty members at the end of the talk. So please ask questions to get the discussion lively. So what I'm going to talk about is we'll start off by getting some lessons from the past. What I have found is, it's always good to study history because there are a lot of lessons you can learn that are going to be very, very relevant for the future. Then we'll move on to the current and really sort of hopefully bring home the point that what we're going to be doing in future is not parallel programming. We're going to be doing sequential programming, but parallel execution. So let's go back about 25 years ago. In the mid-'80s, late '80s, there was a lot of debate as to, how are we going to go beyond the simple pipelined, what people called RISC microarchitecture at that time. There was a desire to do more than one instruction per cycle, and there were sort of two models, the VLIW EPIC style and the out-of-order superscalar style. The VLIW EPIC style, a lot of pioneering work was done here, by the way, in Wen Mei's group. But it started out really as a descendant of high-performance computing. The first, they weren't called VLIW processors at that time, were like, the floating point systems, arrays, or even before that, the color scientific and so on like that. They were really trying to, target scientific computing, which the high-performance people were addressing for a while, but really try and take it down to the processor level. You were trying to search for independent operations, and there was a lot of work done in developing compilers to be able to do that. And then once you had determined what you wanted to do, where the independent operations were, you were going to express that independence in a static program. Okay, so you have an application, you have an algorithm, you have a program, and you have hardware on which the program is going to be run. There's parallelism in the application, the algorithm, and what the approach was to take all that parallelism and express that parallelism statically in the program so the hardware could do things in parallel. Okay? And there was a big strive for efficiency. Well, I shouldn't say, there's a big strive, but, really, there were also very, very clever techniques to, polycyclic scheduling. One of the former Illinois faculty members, a giant in the field, Bob Rao, came up with this wonderful technique, and, software pipelining techniques and so on, really to try and saturate a resource. Okay? So the efficiency notion of, I have efficiency in quotes over here because really the notion of efficiency was, I want to try and eke out the most performance I can out of my hardware. So when you try and create a static parallel representation, it introduces several problems. And there was a lot of wonderful work, dealing with how to solve some of those problems. A lot of it done over here. How do I statically schedule loads? How do I deal with exceptions? All those kind of wonderful work over here. A lot of research. On the other hand, there was a small, group doing out-of-order superscalar processors. It is not from the high-performance computing school. In particular, one of the big innovations in out-of-order superscalar processors were very, very elaborate branch prediction techniques. And that clearly is a influence from non-scientific code. Importantly, there was never a desire to statically represent the parallelism. Okay, the parallelism, you had parallelism, but you never tried to create a statically parallel program. Your program was statically sequential. And in fact, you could actually argue later on, you could actually argue is, the kind of program you wanted to execute on a superscalar processor was one where all the instructions that are close by were dependent on each other. Okay, they were not independent. Okay, and in fact, later on, as people tried to evolve towards, clustered superscalar processors and all these kind of things, try to optimize value passing and the like, they really were leveraging the fact of the notions of dependence. So the out-of-order superscalar world, you created a dynamically parallel execution from a statically sequential program. And when you try and do things dynamically, you have accurate dynamic information. More importantly, you can create a parallel schedule that's very flexible and that is adaptable to the current dynamic runtime situation that you have. Okay? Of course, you have to have parallelism in the application in the algorithm. Okay? But you don't have any of the problems that are there with trying to statically create a parallel representation. All right? Now, if you compared a superscalar and a VLIW processor, arguably, a VLIW processor is quote unquote more efficient by some notion of efficiency. Okay? Because the superscalar processor has all this extra hardware to do this dynamic data flow execution. And it's very, very difficult dynamically to sort of saturate a resource like you could do with polycyclic scheduling or modular scheduling or whatever it is. Okay, and in fact, when Bob Rao would give talks, he would throw out this slide that had only zeros and ones on it. And he said, well, decode the set of instructions. Okay? And well, the hardware is going to have to do some work, whereas the compiler could have done it. There was none of that extra hardware to do that work. Okay, but all that, one of the reasons why the superscalar processors, in a sense, really took off was the interface to the hardware from above. Is very, very simple. It's a natural sequential interface everybody was used to. Importantly, a dynamic schedule is much more adaptable to runtime uncertainties. Okay, so you have, suddenly a piece of hardware go bad, everything will still work fine, albeit at a reduced level. You want to turn something off, it'll work fine. So if your resource pool is changing dynamically, a dynamic schedule is the way to go over a static schedule. So what are some of the lessons? I'm only going to highlight some of the lessons that, to take away from that historical experience. The first thing is, when you think about parallel computing, it is natural to start off from high-performance computing and see how you can apply the wisdom of high-performance computing down. Okay? Is this a good idea? It's not an obvious yes or no. Okay? Furthermore, hardware efficiency may not be the best notion of efficiency. When hardware was at a premium, yes, saving hardware was fine. That was a good thing. But you're going to have more hardware than need to know, than you know what to do with. So one has to revisit what you mean by that notion of efficiency. But most importantly, that you could get a parallel execution without a parallel representation. Okay, albeit at a very small scale at an instruction level. Some other lessons is that a dynamic data flow style of execution is much more adaptable and it's much more flexible than a control-driven execution. So as superscalar processors evolved, you could add in new forms of speculation. You could have different underlying resources, and the execution model, you don't have to do anything in the static program to sort of deal with all of that. And finally, the overheads for achieving that, maybe they are worth it. In this case, it has been shown that the overheads are worth it. So the takeaway is, You may have some overheads, which may sound a little complicated and daunting, but they may be worth it in the long run. There could be hardware overheads, there could be software overheads. Okay, and going forward, we'll have software overheads. So some other lessons is to statically representing dependence may be better than representing independence. Okay? If you know how operations are dependent, you know how they are passing values, you can optimize for that value communication. Okay? You can minimize, you can minimize any resource assumptions you have in independence. And in fact, and I'll try and drive that home further, is if you're looking for independence, the first step in looking for independence is to learn about dependence. Okay? And if you statically want to represent parallelism, you're likely to create lots of problems that are hard to deal with. Of course, a lot of wonderful work done in dealing with those problems, but still, that doesn't make them easy to deal with. There are many other lessons we learned, but I don't have time to talk about all those sometime. Yeah?
Sure. So on the previous slide, the 2 points that you had on the previous slide somehow in my head seem contradictory to each other, right? Because when you say statically representing dependence, you're in some sense statically representing parallelism, because dependent instructions cannot be executed in parallel. And maybe I'm not misinterpreting what you're trying to say.
Okay. The question, this is for the recording. I have to repeat the question. The question is that, am I saying something contradictory over here, where I'm saying, well, by saying that I'm statically representing dependence, am I not saying I'm representing independence? No, that is not necessarily the case. I may have a notion about a dependence relationship between a certain set of operations. I can represent, if I may choose to, I may represent that somehow. But I may have no notion of how different sets of dependent operations interact with each other. Okay? It's a very important difference. And and I'll come to that just in a little while again. So now, we've been at this multi-core generation for about a decade. And, there's a big question. How are we going to get parallel execution on these multi-core processors? There are all sorts of articles saying, hey, unless we solve this problem, industry is going nowhere, industry is dead, and so on like that. Okay, so what we have done is we've gone to our 4 decades of conventional wisdom about parallel processing. And what that tells us is, hey, you have to create a parallel program. You have to create a program where the parallelism is expressed statically. Okay, let's go about doing that. It's very simple. All of us know A, B, and C. All you have to do is A, B, and C. Okay, what is A? You have to analyze the program to identify the independence in the program. And again, the first step in identifying independence is identifying dependence, because those are the independent operations we want to execute in parallel. Then we take that knowledge and create some static representation of the independence. And to satisfy those assumptions, we have to have some kind of synchronization. That's B. Okay. Then, once we have created the static representation, the dynamic execution unwinds as how we specified the static representation. And there can be some potential consequences due to static assumptions, race conditions or whatever it is and the like. The other consequences, as we will see in a little while. Okay? So again, it's very simple, A, B, and C. People have been trying to do this for 4 decades or longer. A lot of very good work done and a lot of progress achieved. Yes, Steve?
Just to give you a hard time and follow up on the previous question, you can recast B as synchronization is there to enforce the dependencies that you identify statically. Right? So there's a little bit of a back and forth between whether you're explicit about your independence or explicit about your dependence.
Okay, so the question is again a follow-up to the previous one about, I could say that part B is really enforcing the dependence, where creating the static representative independence is really enforcing the dependence. Yes, that's absolutely correct. So, there's nothing wrong with what's the issue here. I still have to learn. I have to learn the dependence. Then I have to learn the independence. and then I have to satisfy the dependence in my notion of how I'm going to execute the independence.
I guess the earlier question I took is you were trying to differentiate the difficulty of specifying independence as opposed to specifying dependence. And in some sense they are. I agree with you that they're.
You have to do the second, you have to do the first. One's a subset of the other, I actually would say. We can take this offline, okay? But I mean, the point being over here is, I'm not going to want to do B and C. I don't even want to do all of A. I only want to do part of A. And that part of A is have knowledge about dependence relationships. Or I may not even want that, frankly. Okay? So, just like the BLIW epic, this canonical model creates a variety of problems in A, B, and C. And a lot of good work has been done, a lot of it done over here in solving those problems. I don't, like dealing with complicated problems. I only like to worry about simple things. So let's see how we can do things simply. Okay? Well, if you take a look at it, the parallelism that you're going to get, regardless of what you do and how you do it, is going to be operations on disjoint sets of data. Okay? When you create a statically parallel program, the representation is typically a control-driven program. Most, if not all, practical programming languages use that. Okay? Let's not go into a discussion of functional languages and all that kind of jazz. Okay? And one of the lessons that I have learned over the years in 3 decades is there's a lot of wonderful work being done by people. What you do is you try and learn from what they have done and see how you might be able to adapt that knowledge, fundamental knowledge that they have created, in a different context. Okay? So we are going to try and adapt many of these basic parallelism principles that are there in a way that I happen to think is more practical than the other existing approaches. Okay? So static representation is typically control-driven. Importantly, many of those static representations, they sort of merge together the parallelism in the application and how you want that parallelism to be executed, how you want that execution to happen. Okay? Data-driven focuses on data dependence. It naturally separates the operations on disjoint data, and it can easily be derived from a total order, a sequential order. I'll show you how we do it in a couple of different ways in our context. Going back again to history, VLIW is sort of the static control-driven parallel, and out-of-order superscalar is data-driven from sequential. So I honestly believe that future execution is going to rely very heavily on a data-driven execution, okay, because such models are much more powerful in a variety of ways, many of them that I touched upon in the previous historical context. And the question really is, how are we going to get such an execution model for future hardware? Okay? Now, before we figure that out, let's sort of postulate as to, some other parameters of computing systems, 5-7 years from now. I think everybody's in agreement that we'll have multiple general purpose processing cores. There's still debate whether you'll have, single type of core, or you'll have 2 different types of cores, a big core and a skinny core and things like that. I am a believer that even though you can have statically similar cores, you can have dynamically dissimilar cores, because what makes a core do what it does is not the execution resources, but the state of its dynamic state, the state of its predictors, the state of its caches. Okay, 2 identical cores could perform very differently if they had different predictor state and different cache state, for example. So I call that sort of more a dynamically specialized piece of code. Of course, there'll be some accelerators. The nature of accelerators really sort of types of accelerators I don't think is very relevant. They're going to keep changing. Okay. We are also going to have what I refer to as over-provisioning of cores. And let me see how to put that. So forget about this talk right now, and I'm going to change context for a minute or two, but not any longer, because this subject is a subject of a couple of talks in itself. Is if you take a look at how we've historically employed the Moore's law transistor bounty, is our primary goal was I want to get performance, so I use those extra transistors to get performance. Okay. Now going forward, I'm going to have more transistors up until the point we don't have any more transistors, but our primary goal isn't performance, it's energy and power efficiency. Of course we want the performance, but the energy and power efficiency are more important. So it seems natural to use more transistors to get energy and power efficiency. Well, that sounds like a paradox, okay? But you can actually do that. Okay, what you can actually do, you can have more cores than you know you can possibly power up. And each one of them gets dynamically specialized for a certain type of computation. When you have that type of computation, it's not an accelerator, it's not a GPU, it's the same unit core. Okay, you can turn it on for that type of computation, turn some other core off, and when you move to something else, you keep doing that. Now, regardless of exactly how that pans out, okay, what the bottom line is going to be is the hardware resources in my chip are going to be constantly changing. Okay, so the program that I write is going to have to be able to execute on this constantly changing pool of resources. Okay? Further, I'm going to need to optimize storage of values and how values are communicated. Okay? And again, communication of values, dependence. Okay? So we're going to have to work about that. And this is also something that people are becoming comfortable with these days is, there probably are going to be some software layers to hide the details of the underlying hardware from the application software. Okay? So, meanwhile, let's see what's happening above the hardware. Yeah, Giuseppe.
So it seems you're going towards a data flow model. Do you like anything about the hardware proposed for data flow machines in the last 20 years?
The question is, sounds like moving towards a data flow model. Do I like anything about the data flow machines that have been proposed in the last 20 years, more than 20 years, 30 years? I like everything about them. Most of them I like the ideas they have generated. Now let's figure out how to do it practically. Okay? All right. Okay. So, meanwhile, what's happening is, software is everywhere. Okay? People are writing, big teams of people are writing software, and programmer productivity is becoming paramount. Code efficiency is less important. And if you've gone to school in the last 20, 30 years, I think these concepts have been really hammered into you. Modularity, abstraction, encapsulation. What you want to write code is you want to write code as a module, where you deal with the module via interfaces. You don't care how the internals of the module are implemented. Okay? What we're going to do is we're going to say, okay, I'm going to deal with a module of code with how data flows in and out of this, again, via the interfaces. I don't care when it's executed or where it is executed, as long as I get my data flow right. Okay, it could go execute on a little GPU accelerator. It could go execute on this other core. It really is irrelevant. I really don't care. I just care about the flow of data. Okay? And furthermore, object-oriented programming principles and languages are becoming ubiquitous. Okay? So, my feeling is, well, okay. I think let us separate on what we can sort of agree upon and then what I feel further on top of that. I think we can agree that, you know, people going forward are going to write code with heavy use of abstraction and encapsulation. Okay, just, you know, modular programming style. It's a good thing. Okay, you don't write pieces of code that you expect somebody else to use that has some effect that only you know about that the other person doesn't. Okay, or, you know, if you know about it, at least, you know, you know how to express that effect, though you may not know how that effect may impact something else. Okay. All right. Then I further feel is, hey, if I can write sequentially and get parallelism, why do I have to bother writing in parallel? So I feel strongly, I mean, people know how to write sequential code. Okay, so if you want to, if I can get speed up from a sequential code, why not keep writing sequential code? Okay, of course, one thing we have to do is we have to have him use a parallel algorithm or not artificially sequentialize the code. Okay, oh, sorry, no. Not artificially constrain parallelism. Okay, so, you know, you're trying to, you don't want to use a, you know, you're trying to do a, you know, sum of n variables. You want to use a tree, summation tree, rather than a sequential summation. So we do not want him to statically express parallelism. That's not something people, yeah, well, no, that's what people have been trying to do for years, solve that problem. So how are we going to make it work? So, you know, abstraction's a friend of software. We all agree upon that. What I feel is we're going to help abstraction help us use future hardware. So in my view, a program is going to be a collection of computations, abstractions of computations. It's going to be a sequential representation, which are going to be executed dynamically on a heterogeneous pool of hardware resources in a data flow manner. Okay, I'll show you now two different ways of doing it, and both these these systems we have working, and we run programs on real machines. I'll show you the result from that. They're still benchmark programs, but you know, hopefully by the end of the talk you'll be convinced and run out and try and work with this. Okay, I still have half an hour. I think I'm making fine progress. So we want to get a data-driven parallel execution from a sequential program. If we do that, we can get determinate race-free execution. We have no locks, no explicit synchronization, and, you know, it's going to be easier to write and debug because you aren't doing anything more than what you would be doing for the equivalent sequential program. So how do we do it? The big picture is the following. So we're going to write our programs in a, you know, well-structured object-oriented style. And on our first version, you write methods that operate on the data of the associated object. This is a very common style. Then what we currently do is we identify methods that we may want to potentially execute in parallel in a data flow manner. This is not something you have to do. This is something easily a program analyzer could take care of later on, and we are working on those as we speak. Okay? You do not impose how parallelism is going to get executed. Then what you do is you have a sequential, your program sequential, so you have a thread walking through your sequential program. When it sees a method, it determines the data that that method is going to be touching, and then it queues that method in something that we call a serializer. Okay? It's a bin. And for the program, thread assigns that selected method to a bin in a determined sequential order. So they line up in this bin in determined sequential order. So you're going to serialize the computation to the same object, okay? Assign them to a different bin, and then you have a delegate thread execute these methods from each bin. You don't ever look for independence, okay? You are only trying to enforce the dependence, and if there is independence, it falls out naturally as a side effect, because computations on different bins are going to be on different data, and they're going to execute in parallel. Updates to the state are going to be in the same order as in the sequential program order. So it's going to be a determinate execution. By the way, differences between determinate and determinism and so on. I'm not going to go into them here. You can follow up on them. But there are no races. If your sequential program execution is correct, you will get the same state updates to sequence of state updates to a variable. So your parallel execution is going to be correct for that same input. How do we do it? We have this notion of a serializer, where what a serializer is a queue associated with each object. So whenever you see an operation, a method on that object, you queue it into that serializer. Okay, and you do it via, we have an interface that we call delegate. So whenever we see a delegate interface, we do whatever the runtime does, whatever is needed to stuff that method into that serializer. And then, like in version 1, at times you may wait for all the methods to finish. Okay, in our newer versions, we take it even further. I'll talk a little bit about that. So in the newer versions, you probably won't even going to need these. So I won't go into that. Okay. All right. Now, so you have this notion, and meanwhile, there's another very interesting body of work that has been coming up, which is these task execution systems, where you have a runtime, try and take some tasks that you have written in a parallel program and run them in parallel. Okay. And Intel TBB is one of the most common versions of it. There are many other right now. And you have some efficient scheduling via work stealing, so you can guarantee, so you know how many cores you have, and you can balance load and all that kind of very, very nice things you can do over there. But the program you write still is a parallel program. The objects, the tasks of the parallel program are, of course, run by the runtime system with some very nice properties, but the program you write is still a parallel program. What we do is, for us, each serializer is a dynamic task. So we can have, we can use some underlying runtime system, even though we have our own, but we are feeding the underlying runtime system with this new execution model. Okay? We have a single task for each serializer. A delegation puts a method in the serialization queue, and you spawn a task only if a serializer isn't already scheduled. If a serializer is already scheduled, then you just stuff the new method into the same serializer. So and a task consumes and invokes methods until the serialization queue is empty. Okay, so the one big difference from the traditional task-based systems is our tasks are dynamically changing. Okay.
So what's the difference between the serializer and the bus queue and the queue, the bin?
The Constantine is asking, what is the difference between a serializer and this bin? So you could have different mappings, but the way I described it, I like to say you stuff a method in a bin. So what we actually have in the first version is we have each object has its own serializer. So we have as many bins as you have objects, if you will. Okay, but you could have different mappings. You could map multiple serializers into a single bin, which you may want to in many cases. Okay. So we have a Prometheus library that there's a pthread library. Then we have some runtime system, and Prometheus does work stealing. We have different versions that do something else. Okay, and then on top of it, we have the notion of the serialization set, which is now creating the serializers and mapping the serializers onto tasks to do the right thing. So here are some results we ran.
Can you show us an example program?
No. In a 1-hour talk, when I have so many other things to talk about?
You've been saying, representation is a big deal for you, right? So I'm just trying to understand, what are you representing? I still don't.
Sarita, here. You want to see Matt Allen's 250-page thesis?
No.
There are lots of code examples there.
I just want to see what do you have in your program? It's just a completely sequential normal C++ program, or it's C++ programs plus something else?
What is the plus something else?
I'm
It's the same C++ compiler.
No, but you have some, is the programmer doing anything at all?
Yeah, we say delegate this method for potentially parallel execution. Right now, we need not, once you have a little compiler analysis, you don't need to do that.
But when the programmer says delegate this method for parallel execution, what is the programmer actually saying? I mean, is somebody checking that this is parallel?
What that delegate call does, it calls into the runtime. You compile it, and you get all the templated methods that do the right thing to stuff that method, do the dynamic check, which object is it calling, and stuff that method into the serializer for that object. I'll show you a different code example in a little while. Okay, it's going to look just sequential. It's going to do much, much, much better than sequential. Okay, yeah.
So in something like Charm++, there are objects, and there's a serializer for each object because it's on them, they get serialized, and you said you now have one serializer per object in your current implementation.
Yeah.
What's the
Yeah. So the question, it's a very good question. The question is, how Charm++ has this object and the serializer per object and the like. That's an actor-based system. We have a sequential program. Okay? Ours is a normal sequential C++ program. Okay? Executes on whatever. Okay? Yeah. So, yes, Craig.
When you say delegate this method call, are you saying, is it implicitly saying that the work done by that method call is independent of everything else?
No, no, no. All that I'm saying is this method, when I say delegate this method, I'm saying is this method is going to be operating upon this particular object. Nothing else. Okay? I know this method is a certain property that it's operating upon. It doesn't have, pointers to other objects that are unknown and the like.
So I would love to see this.
Okay?
Sounds like you're guaranteeing independence.
Yeah,
No, I have no clue how this piece of code interacts with anything else.
Can the programmer make a mistake in writing this delegate call?
Well, let's take some. There's actually, this stuff is old. There's some other stuff that is very interesting. Let me get to that. Okay? Because that one's going to be oops. So I want the students to see some of the oops, okay? So that's what we have right now. And here are some results that we have on multi-core machines and some multi-socket machines. But the point being is, we are getting roughly similar levels of performance as a pthread case for these, programs that we have considered. Now, since I know this talk is being recorded, I don't know if they're going to see the slides. Somebody's going to say, how do you get superlinear speedup? That has to do with algorithm data structures that work better as you have more threads than you have fewer threads. That's that's not only for us. That's the pthreads do much better too. So, okay. Now, here's a graph of the scalability that I'm getting for different Prometheus worker threads. Okay. Well, okay. I'm getting fairly scalable speedup, except in this one case where things start getting worse. Okay, this is for us. Turns out you run a pthreaded version of the same thing happens. And that's what the next thing I'm going to talk about is why that's happening and what are you going to do about it. Okay? So the vision so far is the following. The vision so far is I have an abstraction of computations. My program is a sequential representation of the abstraction of computations. And then what I'm going to do is, and I don't care how or where those computations are executed. I just care about the data flow. So I don't know whether I believe that or not. So one test was, let us completely change the underlying hardware that has a very different memory model. Okay? And let us see if what we believe in actually works. Okay, so we bought a Tylera machine. Tylera has 64 cores with cache coherence, nice C++ compiler. And it has a relaxed memory model. So if you're writing programs to a machine with a relaxed memory model, you have to work with nice synchronization libraries, and you have to understand a fair amount of stuff. Sarita can, if you have any questions about that, ask Sarita, don't ask me. Because I've never understood those models. I've always believed sequential was the way to go. Okay, and sequential consistency was the way to go. So
You were on a thesis committee, right?
I know I was. And I told you at that time, Sarita, sequential consistency is the way to go. So I know, because it went in and came out, and I said, oh, I'm learning about stuff I don't understand. It's too complicated for me.
You're being recorded, Guri.
I know. All right, it's okay to say stuff is too complicated for you.
Please.
You know? And the weak memory module stuff is very complicated.
I'm not saying you shouldn't say it, I'm just reminding you.
So what we did is we took our runtime library, and the student initially had some difficulty using the atomics, so he used locks in the runtime because we have these work-stealing queues, and so we were using lock-free data structures on those on those operations. But he figured that out, and it took him about a day to do that. And we do have one place, because of the way we do our work stealing and how we handle all that deck, is we need to write a single register saving and restoring routine. So he wrote that register saving and restoring assembly routine. He put the selected members to deal with those queue operations nicely. And then we used a lot of templated classes, and the compiler didn't have thread local storage for those. So he put his own little storage manager over there. The application code was unchanged. Compile and run. Okay? And this is the performance we got for several of those benchmarks. And what we did is we wrote a network intrusion detection system. It was based on Snort, but not the, so it used all the rule set of Snort, but we didn't use the efficient data structures and the like. Okay, so it's just a test case. And we had our own traces that were derived from our networking group. So there weren't too many flows, and the packets were, there wasn't, some very small and very large packets. But this is not a bad performance for something like that on a machine with a weakly ordered memory system when your code is sequential. By next week, we should have the real Snort running on all of this, because the real Snort is a huge, complex piece of code, but it still uses those nice abstractions and concepts that computer science people have been taught to use for a while. Okay? I'm not going to go into sort of this other one, which my student is doing. We are taking, several of the other Java programs, and now we are putting the concept with a little library on top of the Java thread and JVM pthread library. The point being is, the underlying mechanics of how you execute the code aren't that relevant. Okay, what is more relevant is the model for executing the code. Okay, so yeah, again, we do as well as the pthread versions, and these are all execution times in seconds. But things are going to get more interesting. So let's go to the more interesting stuff. I only have 15 minutes, but let's talk about it. So we can agree that we are going to have multi-core processors everywhere. Okay, but the one big difference going forward is, when we talk about parallel machines, we thought they were a local parallel machine. I understood what the resource of those parallel machines were. Okay, and you know what? When I wanted to run a code, my job on my parallel machine, I used some gang scheduling or whatever it is. So I made some assumptions when I wrote my parallel code, and those assumptions are met. Okay, going forward, we are going to have no clue about the dynamic operating environment on which our parallel code is going to be running. Okay, not of the hardware resource architecture, or not even of the software. I may be running a code, my piece of code, and I make some calls to an operating system, and a version of the operating system that I have on this machine does something yay, and I run that piece of code now somewhere else, and that version is now written to more efficiently do some locking function when I have a few numbers of processors, but not scale when I have a large number of processors. I just don't know what's going to happen. Okay? When I run a piece of code, I don't know which other pieces of code are going to be running at the same time as my piece of code somewhere else. Okay? So when I have a problem like that, it actually turns out, when I have an environment like that, it actually turns out I could have too much parallelism for that current dynamic operating environment. Okay? And you know, that bar we had going down, that was because of that. And I'll illustrate that further now. Okay? Now let me take a very simple piece of code. This is memcopy. I'm just copying a block memory from here to here. Oodles of parallelism. Okay? So I write a threaded version of it, where each thread moves some chunk of code from one location to the next. Okay? I'm going to run it now, and I had 3 different machines I'm going to run it on. One is a machine that has a 4-core processor and 4 sockets. That's a AMD Barcelona that I call 4x4. Another has 4 core processors, AMD Barcelonas, and 8 sockets, so 32 cores. Another is a Intel Nehalem machine with 4 cores, 2 threads per core, and 2 sockets. Okay? I run my same program on it, and I get performance improvement, and then I get a degradation. Okay? In this case, I didn't get a sort of a degradation. In this case, I got a degradation. In this case, I got a degradation. And I got it for different numbers of threads. Okay? And none of them matched the number of processors that I had. Okay? I run the same piece of code now on the same machine, but with different data sizes. Okay? I get different performance peaks for different numbers of threads for different data sizes. Okay? What am I going to do about it? This is just not a good situation to be in the future. Okay? The points of degradation is going to be different. And what's the reason why there is contention in this case for the different machines is the memory controllers. The memory bandwidth capabilities that the Barcelona machines can handle are a little different from what the Nehalem machine can. So, we did not get a performance degradation in the Nehalem machine, for example. So in general, it's because I had created too much parallelism for that resource architecture. Okay? Now, in general, there could be many other resources that I could be contending for. There could be memory bandwidth. There could be software locks in a user program, which again, depends upon how that locking library and stuff like that is implemented on some remote machine. You could get very different characteristics. You could have a lock on a kernel data structure that you have no clue even exists. Okay? And the different benchmark programs that we have actually get degradation for different reasons in each one of these cases. You could have size of on-chip cache issues, network bandwidth issues. You just don't know what the dynamic operating environment is going to be. Okay? What you want is the following. What you want is, once you get to the peak, you just stay there, or you stay near there. Okay? You aren't getting actual performance degradation. Okay? How do you do that? Okay. Well, what you want to do is you want to make sure you don't create too much parallelism for that current dynamic operating environment. Fortunately for us, our program is sequential. Okay? So what you do is you have a single point of control that's unwinding how much work gets executed in parallel. Sorry, I shouldn't say unwinding how much work gets exposed to the runtime, current runtime environment. Okay, how much parallelism gets exposed. So what we can do is we can detect if the parallelism might be excessive. How do we do that? I'll show you in a little while how we do that. And then if the parallelism is getting excessive, you just throttle it back. Okay? By reducing the rate at how you unwind the parallelism. If it's not excessive, then you can increase the amount of parallelism that you have. Okay? And how do we do that? we can establish the notion of some basic, so we can put timer calls before and after each task that we have. So we have some notion of how much time this task is taking to execute. Okay? And then we can monitor the actual rate of increase of that time, of that task. And based on that information, we can control the number of dynamic threads used to execute the program. And I have a lot of, if somebody's taken a copy of the slides, I'll be happy to give them to you. It actually has graphs for different programs that each have different contention resources which cause a performance degradation, albeit a little less in some cases. But we can get to that point and just stay over there. Okay? Now, things become more, so all these runs were, this was when I was running that program in isolation. This is the only program running on the machine. Okay? Things become much more interesting when I have a multi-programmed environment, where I have different programs now running on the machine contending for the same resources. Okay, when you write a parallel program, you don't know what other program might be running with it. So it's going to be very, very difficult to monitor, to actually create a statically parallel program that way. So here what we did is we took 4 instances of MCF, which really aggravates the memory controllers a little bit, and put one on each socket. This is a 4x4 Barcelona machine. And then ran the other benchmark programs with it, p-threaded versions and our Prometheus version. And you can see what happens in each one of these. Okay. Can do much better than the actual p-threaded versions. I have a few minutes left, and now let me tell you about some of the other stuff that we're doing. What we are moving towards now is really a full-fledged data flow system executing a sequential C++ program. Okay? So what we have, a method can have an arbitrary sets of reads, arbitrary sets of writers. Okay? And what we do is we associate tokens with each set of data. And then we annotate the sequential program in our current version, yes, but we are working with the compiler to take care of all of that, to do all those things fairly routinely. We associate tokens with the data. The runtime tracks and resolves all those dependencies automatically. You can actually get a full-fledged data flow execution on it. So I'm going to show you this concept and how simple it allows things to be. This is a very, very simple benchmark kernel example. This is bzip2 compressing, where normally what you would do is you read an input file into some buffer, and then you compress blocks of it, and then you have to write the output to some file. And what you would do is, in a normal threaded version, you would have some code to read the data, and then you'd have the parallel threads to do this, and then you would accumulate all those somewhere, and then you would sequentialize them and write them into some buffer or something like that. My students tell me this is how it is, and I said, fine, you can deal with it. I only think sequential, so show me only the sequential code. Okay, so what the sequential code is, this is where the work is. You're compressing the blocks, and then you're writing the output file to a block. The block to an output file. So this is what our data flow version looks like. You put a annotation, data flow execute, data flow execute. When this data flow execute call is encountered, the runtime system says, OK, it's going to write this block, so it's going to get a read token on this block. And then it goes ahead and schedules that work to wait for it to get a read token. Then you encounter this. This is going to, get a write token over here. Now you need a read token on the block and a write token on this output file pointer. Okay, so when this method is encountered, it tries to get this write token. It can't get this write token until this read token is released. This method releases the read token, but it gets the write token over here. When the next iteration goes around, this method can't get a write token for the output file pointer, but it queues behind that method to get the write token. Okay, so it all unwinds very nicely, cleanly, in a data flow manner from its sequential version. Okay, so we actually have this runtime implementation, and here are the actual performance numbers. on the different cases. All these are, there's no simulation on any of this. This all run to completion, file I/O, everything included. So the speed of numbers include all the file I/O and so on like that too. Yes, Konstantinos.
Yeah, well, Guri, I'm very excited here because you make me feel young again at the risk of sounding self-advertising. Back in 1991, I wrote a paper on multi-programming versus multi-crossing. That was struggling with the same problem. So I feel right on target here. Looking at the trade-off between the compiler or the user trying to maximize the parameters you extract out of the problem, and with the fact that you have no clue what environment you're going to run on. Okay, I'm not claiming I solved it.
Sorry, so this is the previous thing. Yeah, this is not the data flow stuff. This is the other one. Yeah, okay.
But my question there is the problem that I still struggle with is that what you do by floating parallelism is that you defer the problem of scheduling. Right? Instead of a good scheduler should solve the problem. You solve parallelism, speed up, increasing, you reach a plateau, and then you start going down. A good scheduler, and I wish I knew how to tell you what a good scheduler is, but a good scheduler should never allow that to happen. Okay? So by doing what you do, if I understand well, you're floating parallelism, right, dynamically. Essentially, you defer the problem of scheduling with this doubtful mechanism.
Okay, the question is, Konstantinos is saying is that regarding when we had the situation with excessive parallelism, a good scheduler should be able to make sure that doesn't happen. And Konstantinos said he wishes he knew what a good scheduler is. So maybe that is true, but the scheduler and the program are different entities that may not know about each other. The program is dumping this parallelism into the operating environment, which the scheduler is trying to figure out how to execute that parallelism. Okay? So I don't know what a good scheduler might be if it has no knowledge of the static parallel program and how it's dumping parallelism into the operating environment.
Good scheduler fuses the problem, all right? If you have excess parallelism, you fuse essentially the parallelism to only whatever the hardware resources can support. That's the idea.
That's okay, absolutely. The idea is a good scheduler fuses the parallelism to the what the hardware resources can support. And in fact, that's what all these work-stealing schedulers do, and they claim they can do optimal for that, what the hardware parallelism can support. Okay? And their notion of what the hardware parallelism can support is the number of processors that I have. Okay? And not a, I don't know what more you can do as the notion. My hardware resources are going to be completely changing dynamically, as I said. Okay? I also don't know what other program is going to be running. Okay? So while it's a very interesting problem, like you, I don't know how to solve it. Okay? But this works. This works. I just say, look, I'm getting too much parallelism, so I'm not going to create any more work for you. The way we implement the tokens is just another field in the object. We have unlimited read tokens and a single write token. Beyond that, I don't need to do too much more. I will tell you one thing that we are doing, which should be actually fairly obvious if you think about it, is if we had good compiler analysis, we can do away with the token acquisitions, or optimize that aspect of it. Okay, so yes.
Didn't write block, but wrote block 2, made a mistake in the data that's being accessed?
What made a mistake in what?
So the programmer forgot to write block there.
Wrong input
Yeah,
to the
because
function?
It's not an input to a function, right? What you're saying
This
is
gets
that
to be an input to that function.
No, no, no.
It gets an input to the compress function eventually.
Well, but compress could be accessing some recursive data structure, and it could be accessing pointers, and presumably you're asking the programmer to specify everything that compress is going to be writing, correct?
Not necessarily. Yes, in this example, okay, but we have versions where if you have dynamically touched data, you'll still get the tokens for all of that, okay? But then the others that are waiting for those tokens, you can make them wait for unknown tokens. Yeah.
We're having this discussion in the back. Essentially, your df execute is a statement that compress executions are fully independent of one another, and therefore it's an explicit parallel program. Okay, because if it's not, then this synchronization you're adding does not allow it to really execute independently.
Do you call this a explicitly parallel program?
Yes.
How are you going to execute it? How are you going to execute it?
You're asserting that the two executions of
No, I want the underlying mechanics. So you're going to compress and write it to a file right away?
I'm sorry, what are you asking? I'm claiming that your statement, if compress, for example, has static data, then this will fit. So your correctness depends on the implementation of compress.
All right. So I'm going to make a generic statement, which is if you do all these academic things with and that break your normal, okay, that break the ability of anybody else to use a defined interface, okay, that's fine. You're going to fail, okay.
There are many encoding schemes that are fully served. I mean, I don't remember
Hey,
what
okay. If you call this a parallel program, that you're welcome to. I call it a statically sequential program. Does anybody else call it a parallel program? Okay. So your actual program that's running on the hardware is not sequential. Okay, good. I learn something new every time I come to Illinois. So I have learned this is a parallel program. Okay, thank you. So my view, I mean, this is, general purpose computing is going to be parallel computing, but it's going to be very different from this traditional notion of parallel computing, which by traditional notion I sort of talk more about the HPC-derived traditional notion of parallel computing. We are going to require new ways of thinking about how to execute programs. And we want programmers to think parallel, but the program is going to be sequential. I still think that's sequential. If you call it parallel, feel free to. But what we're going to be doing is we're going to be executing the sequential programs in a dynamic data flow parallel manner. Thank you.